I have an example to illustrate how the center of mass can be useful in calculations in physics. Just a little bit of a contrived example, but I also think it's cute. We have a situation where a shell is launched, so it goes on a parabolic trajectory, and it has been arranged that when it reaches the apex of that parabola, the shell is going to explode into two parts, each of equal mass, and we observe that from the apex, the first piece just falls straight down. And our question then, our challenge, is to determine where is the second piece going to land. So there's a few ways we can do this, but I'm going to choose to do it in terms of center of mass. We know that when they land on the ground, the first piece has to land there. If the two pieces had not split up, right, their center of mass would follow a parabola, and they would land at their center of mass. And then where is x2 going to fall such that the center of mass follows just where it should according to the parabola from free fall motion, projectile motion. So we want to find x2, and we're going to use kinematics and projectile motion to calculate where the center of mass lands, and then based off of that, where the first part lands. Use that together to find where the second part lands. And going way back when, we know that the range of a projectile is initial speed squared over the acceleration times sine of twice the launch angle. And so we know all of those quantities. So 20 meters per second, quantity squared. We are on Earth, home sweet home. And the launch angle is 60 degrees, so this is sine 120 degrees. So to 3 decimal places, I get that to be 35.3 meters. And that is where the projectile would have landed had it stayed together. x1 is the x-coordinate of the apex, which is half of this, because we're beginning and ending at the same height, and the free fall motion is going to be symmetric. So again, when I keep 2 decimal places, or 3 decimal places rather, get that to be 17.7 meters. And then we can use the equation for the center of mass to find the unknown x2. So setting it up, x of the center of mass is 1 over the total mass, sum from I equals 1 to 2 in this case, mass of the ith bit times the x-coordinate center of mass of the ith bit. I'm just expanding what that summation looks like. The projectile, the shell splits into two equal mass halves. So each one is half the total mass. And this is x1. And we'll have, again, half the total mass times x2. And then that is our unknown that we're trying to solve for. And we'll observe that total mass cancels out. Don't need to know it. So we have an equation that looks like x, the center of mass, is equal to x1 over 2 plus x2 over 2. Solving for x2, we'll have x2 is equal to twice x of the center of mass minus x1 over 2. And now everything on the right hand side is known in terms of our calculating the range. So you just plug those in for the plug and chug stage. Twice 35.3 meters minus half of our 17.7 meters. And we'll get this coordinate x2 to be 52.9 meters. All right, another way I could have done this, just to lay it out, but I'm not going to work out the calculations, is projectile motion to get to the apex, the point where like the y velocity is equal to 0, hunky-dory. Then at that point, I'm going to have the explosion happen and modify the velocity of the shell that goes forward, particle 2, double its horizontal velocity, and then find where it lands as another projectile motion problem. I'm starting at a known initial velocity. I'll start from a known height, for example, and then you can work out where it's going to land. And you can verify for yourself, you get the same answer. This way of formulating the question in terms of like doubling the horizontal velocity at the apex, that is based on the idea of conservation of momentum. If this half of the projectile has no momentum, if I'm going to preserve the total linear momentum, then I have to double the momentum of the second half. Hence I know that its horizontal velocity doubles. And I can do conservation of momentum along just the x direction, because there are no forces acting left, right, between that first instant after launch till the last instant right before it collides with the ground. Even though gravity is accelerating the object vertically, there's nothing acting horizontally, so it's an object that is isolated horizontally but not isolated vertically. So either way, it's going to give you the same answer, so you can verify for yourself. But I think it's cuter to use the center of mass as the means of solving it.